You just get ready. I don't know when is it.
All right.
Okay. So it will be on chapter 4 lah. That means from chapter 4.1 until chapter 4.5. Okay. Just get ready with it. Okay. So let's just start for the 4.5. Is everyone okay? Ready?
Ready? Yes.
Yes, madam.
Yes, madam.
All right. So chapter 4.5 is quite a short chapter. So over here, let's look at your learning outcome. We're talking mainly about metallic bond. Okay, so we want to explain the formations of metallic bond using our Electron C model. Okay, this one is very important. Not Electron C model. I will guide you how to draw the model. Okay, and then B, relate the metallic bond to its properties of metal. So properties of metal including malleability, ductility, and electrical thermal conductivity. And then after that, we want to explain the factors that affecting your strength of metallic bond. So over here also, when we talk about strength of metallic bond, it will link it to your boiling or melting point. Okay. And then last one, to relate melting or boiling point to the molecular structure, type of bonding, and intermolecular forces. And we want to talk about period 3, group 1, group 17. Okay. So first of all, metallic bond. So if you still remember our overview for the earlier 4.4, we have the metallic bond inside intramolecular forces. Okay, intramolecular forces. But metallic bond is something special. That's why it has its own subtopic. That means when we talk about metallic bond, it can refer to intramolecular forces. It can also refer to intermolecular forces. Okay, so metallic bond, they have their own property. Because metal, they have only its own molecule. Okay, so let's just look at in detail. So metallic bonds over here, it refers to the electrostatic attraction between the positively charged metal ion and the sea of delocalized valence electron. So instead of you have only one metal and one ion, we are looking as a whole thing. Okay, we are looking at the individual metal atom, metal ion, and the sea of delocalized electron. Okay, so this one is the definition of your metallic bond. Okay, so if you look at the diagram over here, you see in the bigger circle inside here, you have a positive charge. That is a positively charged atom of your metal. Okay, or your metal atom or your metal ion. So they refer to the same thing, metal ion. Or sometimes it's called metal atom. So the sea of electron represented by the valence electron. So say if we got sodium, you have one valence electron. If you have magnesium, then we have two valence electron. So the describing of this electron C model, you will see it over here. In the solid state, the metal atoms are packed as close as possible. So we put it inside a fixed positions for all these metal ion. Okay, so all this metal atom or ion in the sample contribute their valence electron to form an electron C. Okay, that is delocalized over the entire solid. We already represent by this squares only. Dalam square ini saja kita tengok, bukan satu whole structure lah. You only need to draw this model. So what it means by delocalized, that means the electrons are free to move around. Okay, in another word, we can say mobile electron. Maksudnya delocalized lah. Localized, that means the position is fixed. Delocalized means the position is not fixed. So this sea of valence electron is acting like the glue, okay, holding the metal ion in place. That's why the metal atoms is present as a solid. Okay, so this one is in general idea only of your electron C model. But you have to know that how to draw the electron C model following the metal. Okay, so if you look at the diagram below here, we have sodium and also magnesium. Okay, look at sodium first, yeah? Okay, we know that sodium is coming from your group 1. So each sodium atom will release one valence electron to form your Na positive. Okay, and then the electron will go into the sea of electron. So to form a sea of electron, a sea of delocalized electron. So this point is very important because you refer to the metallic bond. So metallic bond of the sodium metal is the electrostatic forces between the Na positive, our positively charged metal ion. So in this case, kalau sudah tahu metal apa, mesti kena mention lah dia punya simbol Na positive, the positively charged metal ion. And the sea of delocalized electron form this metallic bond. So if you can see over the model over here, dalam satu kotak kita letak 9 circle saja. If you want to put 6 also no problem. Okay. And then the number of electron, it should be the same as your number of Na positive. Okay, so if let's say over here we have 9 ion of Na plus, we have 9 valence electron at the same time. So if let's say over here, let's say we take the metal potassium. Okay, so you need to learn how to draw the electron C model. Say we have again 9 atom, okay, or 9 circle over here. So inside that circle represented by a K positive. Since potassium also in group 1, we have 1 valence electron. Okay, so each of the potassium over here, they will attach, or around that it will have 1 valence electron. So satu ion potassium, satu valence electron. So awak kena samakan bilangan dia. Tak kisahlah awak letak mana. Asalkan bilangan dia sama. So 9 over here, 9 ion, you are going to have 9 valence electron. So until here, can you follow?
Yes.
Okay.
Yes,
So if
madam.
you want to explain the metallic bond for potassium metal, we will say the electrostatic forces between K positive and the sea of delocalized electron form metallic bond. So penerangan yang spesifik adalah dia punya positively metal ion, K positive. So dekat sini lah yang ini yang general, yang ini yang atas ini adalah yang general. Tapi kalau sudah tahu metal, kena masukkan simbol metal sekali. Okay. So if we look at the second example here, we have magnesium. So we know magnesium comes from your group 2 valence electron. Okay. So each magnesium atom release 2 valence electron. Okay, and then electrostatic forces between Mg2 positive and the sea of delocalized electron form the metallic bond. Okay, so dalam sini, dalam awak punya diagram, can I know how many ion of Mg2 plus we have got?
18.
Ion?
9.
Oh, that's electron, sorry.
Yeah, Mg2 plus, we have 9. Okay, we have 9 ion of it inside your model. So the number of valence electron you have to follow. Each of them providing 2 valence electron. So in total, number of valence electron should be 18. So kalau awak kira bilangan elektron yang ada dekat sini adalah 18. Did you get it?
Yes, madam.
Okay, so let's just try to draw the Electron C model for aluminium. So how was it? Aluminium have how many valence electron?
3.
Yes, 3 over here, right? So inside your diagram, you will draw something. The circle is more or less the same. Okay, we have Al3 plus, Al3 plus, and each of every one of this you have to label. Okay, semua kena label sekali Okay, so bilangan elektron ada berapa? How many electrons altogether if I providing 9 aluminium ion?
37.
20?
27.
7, because each of the aluminium providing 3 valence electron. So bila awak lukis, kena pastikanlah awak ada bilangan elektron. So number of your valence electron is 27. So kena penuhkanlah awak punya elektron dekat sini. Okay. So the electron now is becoming more and more. That means this valence electron forming kind of like a C. When we say a C, that means these electrons are mobile. They can move around. Electron ni boleh bergerak sampai sini. Electron ni boleh bergerak sampai sini. Okay, so we are describing this mobile electron as a C electron. Okay. So until this part, can you follow? Boleh lukis lah. Lukis sekali. So penuhkan awak punya electron. Make sure it is 27. Okay. Boleh ikut
Boleh, madam.
Okay, so madam tunggu sekejap awak copykan dia punya Electron C model.
Madam, apa kedudukan elektron tu nak lukis macam-macam mana pun boleh eh?
Macam mana pun boleh. As long as bilangan dia betul. Tapi the best you just put your electrons around the ion. So make it look like a C. Jangan awak statickan semua elektron satu barisan. Janganlah sebab elektron is delocalized. That means they are free to move around. Okay. Dah siap boleh bagi tahu madam So madam boleh proceed kepada yang seterusnya.
Dah, madam.
Okay. This topic, chapter 4.5 also quite a lot of explanation. Similar like 4.4, a lot of explanation. So our second part of 4.5 is the property of metal. So property of metal dari is from the appearance of physical properties. Over here we can say it is shiny. Or another word we saw is lustrous. Hold on a second, yeah. Okay, so most of the solids, they have moderate to high melting point and they have higher boiling point. Okay, it can be bent or dent rather than crack or shatter. Dia awak tak boleh pecahkan metal tapi awak boleh tukar bentuk dia. Now, you can bend it, you can dent it, but it won't crack into pieces. Okay, and then on the third point over here, we have malleable. So the meaning of malleable, it means that you can flatten or you can change the shape of metal into sheet. Macam satu lapisan metal, aluminium sheet, copper sheet, macam satu lapisan saja. So kita tukar bentuk dia. Okay. The properties can also be ductile. Malleable, ductile, you have to be able to differentiate them. Malleable, that means flatten into sheet, and then for the ductile is to pull into wire. For example, your copper wire. Okay, and then last one is it can conduct heat and electricity both in solid and liquid state. So over here, when you see something like this, when madam say aluminium, over here inside your bracket I put liquid or liquid and molten. Refer to the metal in the molten state. Liquid maksudnya molten lah dekat sini boleh highlight kan. Bukan liquid maksudnya dia cair, tapi cair dia masih attached lagi. The atoms of metal is still attached together. So molten is more easy to understand. So this one refer to molten state. Okay, so boleh catat liquid molten is the same thing. So over the three boxes here is explain the properties of your metal, each of them. So first of this is why the solid metals are with moderate melting point. Dia punya melting point tak tinggi sangat lah. It's not like very high. One of the reason is because you do not break it. You only try to bend or change the shape. So over here you see attractions between metal ion and the delocalized electron do not need to be broken during melting. Okay, therefore you have only a moderate melting point. But if in terms of boiling point, you have a higher or slightly higher boiling point, because when we talk about boiling point, we want to break the intermolecular forces. Remember in our previous subtopic, boiling point refer to the intermolecular forces. Okay, so if you got a stronger metallic bond, you will require more energy to break the bond. Boiling point, breaking bond, melting point, you only change the shape only. Okay, so that refers to our explanation of melting and boiling point. Then the next one, why metal can conduct heat and electricity? So the only reason is because of the C of your valence electron. So due to the presence of mobile or delocalized electron. Or maybe you want to mention due to the presence of electron C. Pun boleh. Dia mentions benda yang sama, electron C. Okay, and then last one over here, why metals are malleable and ductile. Okay, if you look at the diagram below here, the first diagram over here refer to your metal. So in between, madam is talking over here. Yeah. Wait, now hold on. Okay, I'm mentioning about this one. Your model in the bottom here. Okay, so metal atoms are closely packed in fixed position. Or maybe you want to mention metal ions, both refer to the same thing. Okay, so when it is deformed, your metal ions slide past each other through the sea of electron. So kalau awak cuma ketuk dia saja, dia tak ada break bond. Dia cuma tukar shape. So sliding past each other. Okay, so until step B over here, you just change the shape. Okay, so change in new positions of metal ion causes redistributions of the valence electron, therefore forming new shape. So kenapa kita perlu belajar Electron C Model supaya kita tahu elektron ni sebenarnya dia macam glue, dia macam satu bentuk cair. So when you change the shape, you will not break the bond, but you only sliding the metal ion. So electron dia akan ikut shape dia lah. So you are not breaking the bond, and that's why we have a malleable and ductile property for metal. But if we compare with the ionic compound, yang ini comparison ya, VS. Comparing with ionic compound, we know the ionic compound is between cation and anion. Dia bukan sama dengan electron. Dia ialah cation, anion, cation, anion. So looking at the model over here. So why we say ionic compound crack or can break into pieces? Because when you knock it, okay, you hit it very hard with some external forces, you will change the positions of the ion. Yes, but then until one point, you will see the positively charged cation positions at the same place. So we know that positive and positive, they will repel. Negative and negative, they will repel. That's why ionic compound, they will crack, they will break into pieces, but the metal will not. Because metal structure, they have the sea of electron. So ini cuma nak bagi perbandingan antara metal dengan ionic compound. So until this point, can you understand?
Yes, madam.
Dia cuma satu theory sajalah untuk to describe your properties of metal. So can read through on your own, yeah? Okay, the much more important topic over here is to compare the strength of metallic bond as it can link to the boiling point. So remember, boiling point, we talk about intermolecular forces. The stronger the intermolecular forces, the higher the boiling point. So for metallic bond, also we want to compare whether this bond is strong or weak. So there is two factors for you to look around. So first of all, we look at the number of valence electron. Okay. In here you can mention number of delocalized electron, or you want to mention number of valence electron. Dua-dua sama ya. Okay. So as your number of delocalized valence electron increases, the forces of attraction become stronger, which also say that your metallic bond will become stronger. So if you want to talk about boiling point, then we will say the higher is the boiling point. Dia adalah satu synchronized explanation. Okay, so metallic bonds become stronger, the boiling point become higher. The second factors over here, we look at the size. Okay, size of your positively charged metal ion. Again, when I say about metal ion, it refer to the metal atom. Dua-dua adalah sama. Kenapa Madam cakap sama? Kalau contoh. Okay, if we take group 1 as example, we have lithium, we have sodium, we have potassium. So this one, Madam give it as the atom. Okay, but when we look at the ion, also the same thing. Lithium will become smaller than lithium parent atom. Sodium ion will be smaller. Potassium ion will be smaller than potassium atom. But sama juga dia punya train. Going down the group, the size of the size of atomic size increases. Ionic size also increases. So dekat sini size of positively charged metal ion boleh pakai, size of the metal atom pun boleh pakai. Is that clear?
Yeah, madam.
Yes, madam. Clear.
Sebab
Yes,
ada
madam.
Yes, madam.
certain reference book that talk about atomic size, certain reference book that talk about ionic size, but both of this refer to the same thing. Okay, so when we talk about size, smaller the size, closer the distance between the nucleus and your electron cloud, therefore your metallic bond will become stronger. So dia ada kaitan dengan chapter 3 yang awak belajar itu. Now, smaller the size, closer the distance or stronger the nucleus attraction, therefore metallic bond becomes stronger. Okay, so in short, we can classify into the formula like this. Strength of metallic bond is directly proportional to the number of your valence electron, or the strength of metallic bond is inversely proportional to the size. So in short, we can say the higher the number of valence electron, the stronger is your metallic bond. Or maybe the smaller is the metal ion size, the stronger is your metallic bond. So boleh pakailah untuk formula yang simple ini. Tapi priority kita memang tengok dekat valence electron dulu. Bilangan valence electron first. If they have the same valence electron, then only we'll look at the size. Okay, so first one, lithium, potassium, which one have the stronger metallic bond? The example here is not in the notes. You can copy down the example here. Compare the strength of metallic bond between lithium and potassium. Which one having a stronger one?
Lithium.
Lithium. Why lithium?
Smaller size.
Has smaller size.
So both lithium and potassium, they are coming from group 1. So they have the same number of valence electron. Jadi untuk faktor pertama kita tak boleh pakai. Strength of lithium is stronger than potassium. Why? Because the ionic size or the atomic size of lithium is smaller than potassium. Okay, now buat ayat sendiri pun boleh lah. Lithium has a stronger metallic bond because it has a smaller size compared to potassium. The smaller the size of metal ion, the stronger is the metallic bond. So size dengan strength dia adalah inversely proportional. Okay, how about if I compare between sodium and aluminium? Which one having a stronger metallic bond?
Aluminium.
Aluminium. Why aluminium?
More number of valence electron.
Yes, number of valence electron of so Madam tulis ya, boleh salin. Number of valence electrons of aluminium is more than sodium. Ingat bila kita tulis explanation, you cannot just give statement. You cannot just say aluminium has 3 valence electron. Sodium has only 1. Therefore, strength of aluminium is stronger. Cannot. You must compare more or less. Ingat bila compare kena guna perkataan yang tentulah untuk comparison, more or less. So number of valence electrons of aluminium is more than sodium. Therefore, aluminium has a stronger metallic bond. Kalau kita nak bandingkan boiling point pun boleh. The higher is the boiling point for aluminium. Okay. Sampai sini boleh ya ikut. Dia lagi simple lah daripada intermolecular forces 4.4. Okay ya? Alright. So you can jot down the answer and we'll proceed to the next one. Okay, let me know if you have done, yeah? Okay. So just now we talk about the metallic bond. So now we want to see overall for your element inside period 3. Masih ingat lagi kan period 3? Yeah, chapter 3 we talk quite a lot for period 3. Ingat lagi untuk elemen dalam period 3?
Ingat.
Okay. So the trend of melting boiling point across period 3 starting from sodium until argon. Okay, so if you look at the table over here, giving you MP stand for melting point, BP stand for boiling point. So we talk about boiling point in this case. Okay, so you see from sodium to aluminium, 892,000, 2004. Okay, so the boiling point increases from sodium to aluminium. Okay, and then on silicon, you have the highest boiling point, 2680. Among all is the highest. Why suddenly becomes the highest in the middle of the period? Okay, you have something to do with the structures. Okay, and then after that, from phosphorus until argon, you will see phosphorus 280, sulfur 440. Suddenly it drops down to negative 34. Okay, and then after that, it further drop into negative 186. So, macam mana kita nak kaitkan kita punya boiling point dengan intermolecular forces mereka? Okay, so inside the diagram over here, Mendel have already write for you. Sodium to aluminium, they refer to the metallic structure. Okay, it have something to do with the structures. Okay, and then for silicon, giant network covalent structure, we will look at this one. How is it arranged for silicon atom? Then for phosphorus until argon is simple covalent structure. So over here, for your element across period 3, the irregular pattern of your boiling point, it depends on the structure. So when the structure is different, we have different type of intermolecular forces. So first of all, look at the metal first. Sodium to aluminium, just now we talked about how the strength increases, right? According to the valence electron or the size. Okay, so from sodium to aluminium, first of all, we have metallic structure. So very easy. When you have metallic structure, you will have the metallic bond. Okay, metallic structure, metallic bond. So the strength of metallic bond is proportional to the number of valence electron. So we know that from sodium to aluminium, number of valence electron increases. Therefore, the strength of metallic bond also increases. So the more valence electron, stronger the metallic bond, higher the melting or boiling point. So for metal, it's similar like our theory just now. So metal boleh accept? Boleh faham?
Boleh, madam.
Madam.
Okay. Second one, we look at silicon. Okay, with a symbol SI represents silicon. Can I know silicon is from which group? Anyone know where is
14.
silicon?
14.
Group 14. Above silicon?
Carbon.
Carbon, right? Above silicon is carbon. So after carbon, we have silicon. But carbon is in period 2, silicon is in period 3. So for this silicon, they will make up a giant network covalent structure. Okay, the keywords over here is giant. Okay, giant network covalent structure. And in these structures, we have infinite number of strong covalent bond. Infinite, if you know about infinity, that means it have countless, it have a lot, it have a big amount of strong covalent bond. So, madam nak awak cuba tengok structure yang ada kat tepi sini. Structure ini awak boleh Google untuk tengok, tapi madam tak masukkan dalam awak punya nota. Okay, just for you to know what it means by giant network covalent structure. Okay, so this structure, giant network covalent structure. It means that for either silicon or carbon, carbon nanti dekat chapter 5 kita akan gunalah untuk carbon, giant network covalent. Cuma sekarang sebab period 3, so we talk about silicon first. Okay, so we know that each carbon or each silicon, they are bonded tetrahedrally. Okay, satu example yang sangat simple. Cuba awak fikirkan, satu carbon maximum minimum mesti kena ada 4 bond. Sebab carbon must be octet. Okay, therefore same thing apply to our silicon. It must tetrahedrally bonded. Okay, so satu atom silicon, it must having 4 bond. So when you have having 4 bond, you are having the tetrahedral shape. Okay, so silicon are arranged in this shape, infinity. So maksud dia dekat bawah sini, dia boleh attach lagi. Lagi 2 kaki, lagi 2 kaki, lagi 2 kaki. Sampailah satu network yang sangat besar. So the structures over here, we only show a few only. Okay, but this refer to your giant network covalent structure. And you must link it to, when you have a giant network structure, you will have a very strong covalent bond. Okay, so when we say about strong covalent bond, okay, in this case, it will link it to a very, very high melting or boiling point. That means you require a lot more energy to break this bond. Okay, sampai sini boleh terima untuk structure silicon. Nak belajar macam mana nak lukis pun boleh. But you have to see from the pictures itself, you need to recognize these structures is the giant network. Okay, and then in the explanation here is already given that melting and boiling point silicon is the highest, okay, due to these structures and the very high energy is needed to break the very strong covalent bond. So please highlight the keyword giant network covalent structure and very strong covalent bond. Okay, so any questions until the part for silicon?
Sorry, madam, I'm not quite understand. Why is it covalent bond?
Sorry, Sue, you're asking question?
Why is it covalent bond?
Okay, why is it covalent bond? So now we are looking at group 14. So if silicon, normally we will talk about intermolecular forces, isn't it? But silicon over here, we are not referring to the intermolecular forces. It's kind of like an anomalous case. Okay, but we will look at the covalent bond because this covalent bond is very special. Okay, because it has the giant network structure. So we are not looking at the van der Waals force or the London forces in this case. Okay.
Oh, so they are like truly sharing electrons with each other.
Yeah, they will share the electron. So between silicon and another silicon, they will share the electrons to form this covalent. But these structures will keep on forming until it forms this network.
Oh,
Uh,
okay.
but because of the structure is too big and too it's very special until we will only consider the covalent bond rather than the intermolecular forces.
Okay.
Okay,
Understand. Thank you, madam.
right. Any other questions until the part for silicon?
Uh, Madam, so silicon is the element that which is amphoteric in the period 3, right?
Amphoteric?
Yes. Am I right? Or is it aluminium? I'm not sure.
If the words amphoteric, that means you refer to amphoteric oxide. If
Yes.
amphoteric oxide, that is aluminium.
Oh, not silicon.
Yes. Silicon, if you want to talk about metal or non-metal, silicon is metalloid. That means half-half. But it has nothing to do over here, lah. But you can refer sodium until aluminium is metal. Then silicon is metalloid. Phosphorus until argon is non-metal.
All right.
Okay? That one is in your chapter 3. Madam boleh tengok balik awak punya chapter 3. So when we talk about that one is in the last one. Okay, so for this part lah, you all can see acid-base property across period 3. Silicon is metalloid, but the oxide of it is acidic oxide. Okay, so over here also Madam included last time, but this one doesn't include in your chapter 3. Madam have already mentioned 4.4, we will look through for the elements in period 3. So if you can see over here, the giant network covalent structure for silicon, yang dua ni salah ni sebenarnya metallic structure, metallic bond. But silicon, giant network structure, you got infinite number of covalent bond. Okay, so we go back to chapter 4. So silicon, remember about the keywords, giant network covalent structure. And then next we have from phosphorus until argon. Okay, phosphorus until argon. Now we go back to the intermolecular forces, our van der Waals forces, or the London forces. London forces. Okay, so from the phosphorus until argon, I want you to remember that for the element when we want to talk about their structure, okay, phosphorus exists as P4. It's not like a single atom phosphorus only. Okay, it exists as P4. So the P4 will look slightly like this. It's not exactly tetrahedral, but you have 4 atoms link it together to make a molecule of P4. Okay, whereas for sulfur, it will exist as S8. Formula ini adalah fix, P4S8. Okay, this is also related to why when we talk about chlorine gas, kita mesti link, okay, mesti F2, Cl2, Br2, and etc. So when we talk about sulfur, you always refer to S8. You talk about phosphorus, we refer to P4. So this is the natural state that we find for phosphorus. Okay, the natural state that we found sulfur. So for sulfur S8, you can see the structure is drawing like this. Okay, this is what we refer to a simple covalent structure. That means until 8 atoms link together inside sulfur, then the structure will stop. Then another 8 will link together to form S8. Okay, unlike your silicon, when you form tetrahedral structure already, it will continue the structure until it is big enough. But sulfur, phosphorus, chlorine, they stop until where they are, S8, P4, Cl2. Okay, but the last one, when you see argon, because it's coming from group 18, it exists as mono atoms only. It will not link with other atoms. So argon exists as a single atom. So dekat sini boleh highlight lah. From phosphorus to argon, it exists as a simple covalent structure. P4, S8, Cl2. Okay, when you have a simple covalent structures, now we go back to the intermolecular forces. Silicon tadi exception lah sebab dia punya giant network covalent structure. Sampai dia tak nampak intermolecular forces dia. Okay, but then for phosphorus until argon, it's not that big. So we still can look at these intermolecular forces. Okay, so for phosphorus, sulfur, chlorine, argon, we have the weak van der Waals forces. Or in another more specific, we can say it has a weak London forces. Okay, so since phosphorus until argon, they are all non-metal. Okay, they are all non-metal. And then they're all having the same type of intermolecular forces, which is van der Waals. Therefore, we can only compare the molecular size. And don't you forget that molecular size linked to polarizability. Okay, we say that the bigger the molecular size, the greater the polarizability, the stronger the van der Waals forces, or the stronger the London forces. Okay, therefore the melting point will go accordingly this way. Okay, you see molecular size, argon is the smallest, but sulfur is the biggest because of S8. You can try to calculate the molecular mass. Then you will see sulfur has the bigger mass. Okay, and then the strength of van der Waals forces increases also from argon to chlorine to phosphorus P4. Then the biggest one or the strongest one, we can have S8. Last one, melting point for sulfur is the strongest. So if you can see over here, when we talk about boiling melting point, we use the element only. But when we look at the structure, okay, we want to talk about the forces, we will talk about the structure. So which structure is belong? Is it metallic structure, giant network covalent structure, or simple molecular structure? Okay, so until this part, is everyone okay? Nampak susah sikit kan? Tapi dia hanya untuk period 3. So now we are focusing on period 3. Is that okay?
Okay.
Kalau berbanding daripada chapter yang sebelum ni, let's say we talk about chapter 4.4. We want to find the intermolecular forces. Jangan lupa, soalan yang sebelum ni, dia adalah compound. Contoh, alcohol, CH3OH. So from there, we can see what is the intermolecular forces. Okay. Or example, if you see HF. So dia adalah salah satu molekul. So kita dapat nampak intermolecular forces dia apa. Cuma dekat sini period 3 semua adalah elemen. So we have to know inside the elements over here, actually, if you put sulfur and sulfur together, then how about its boiling point? Phosphorus and phosphorus, what about its boiling point? So sekarang ini awak bukan nampak satu compound tau. Ini adalah elemen. So we have to see what is the structures they have got. Kalau tak faham, madam buka balik contoh yang sebelum ni. Kalau awak tengok exercise sebelum ni, semua adalah compound. So very easy for you to look for the intermolecular forces. Is it dipole-dipole? Is it London forces? Is it hydrogen bond? But when we come into the element period 3, we have no idea. Then we have to find out what is the structure if I put silicon and silicon together. Okay, phosphorus and phosphorus together. Sulfur and sulfur together. So jangan confuse dengan apa yang kita belajar sebelum ni. Itu adalah compound. Sekarang ni adalah elemen. So bila ceritakan period 3 element, sodium to aluminium. Okay. Sodium and sodium form metallic bond. Aluminium form metallic bond. Silicon, giant network covalent structure. And then phosphorus form P4. Sulfur form S8. Chlorine form Cl2. And then argon S atom. Okay, so I also put a link over here for your reference for giant network covalent structure. Okay, so you may access for this one to see what it means by giant network covalent structure. We will come back to this network structure in our chapter 5.3. Akan patah balik kepada ini untuk ceritakan selain silikon, carbon pun boleh jadi giant network covalent structure. So that one it will be in your next chapter over there. So this one is your extra reference, yeah, for those who want later, madam share link into your Telegram group. Okay. So any question for the train across period 3? Tak ada soalan, madam continue ya. Is that okay? Okay, this one is from your learning outcome, the last one, right? You want to explain the trend of melting point, boiling point across period 3, and then you want to explain for group 1 and also group 17. So the trend of melting and boiling point going group 1, because we know that group 1 is metal. So it has something to do with your metallic bond. Or if the questions ask about group 2 also, we can use the factors affecting strength of metallic bond. Okay, so try to fill in the blank space over here. Group 1 contain?
1 valence electron.
Okay, 1 valence electron. So going down the group from lithium to cesium, the atomic size
Increase.
increases. Okay, as you got more shell, you got more shielding effect, the size increases. So the attraction between nucleus and your sea of delocalized electron becomes weaker as the size increases already, yeah? So how about the strength of, what are we talking over here? What is the type of bonding we have got for metal? Strength of metallic bond. Okay, so the strength of metallic bond between atoms becomes stronger or weaker?
Stronger.
When the size increases, the strength becomes weaker. This one go back to 4.5, the earlier just now. Strength of metallic bond is inversely proportional to the size. Size, it can refer either you want to talk about atomic size or ionic size. Sorry, size of atom or ion. Okay, so when we have a bigger size, you have a weaker metallic bond. So the strength of metallic bond becomes weaker as the size increases. Then what happens to the melting and boiling point? Is it increases or decreases?
Decrease.
Decreases. Okay, strength, boiling point depends on strength. So strength becomes weaker, therefore your boiling point will decrease from lithium to cesium. Okay, trend of melting and boiling point going down your group 17. So group 17, if you look at the element, period 2, we have fluorine, then chlorine, then bromine, then iodine. So if we want to talk about the boiling point, we will first look at the structure. Okay, so fluorine as is F2, Cl2, Br2, and I2. So we know this, all of them are non-polar molecule. Okay, non-polar molecule. So over here, yeah, F, Cl, Br, and I exist as molecule of F2, Cl2, Br2, and I2 respectively, and has only weak. What force do they have? Okay, so over here you can also jot down London force or Van der Waals forces. Both are accepted because London force fall into the category of Van der Waals. Okay, so molecular size
Increasing.
from
Fluorine to iodine.
fluorine to iodine. So if let's say you want to use words, you can use word. If you want to use symbol, yes, no problem. F2 followed by Cl2, Br2, and the biggest go for the iodine. So sama jugalah kalau awak tengok elemen atom saja, fluorine is the smallest, iodine, the atom is the biggest. So when you talk about the structures, F2 is the smallest, I2 is the biggest. So size going down increases. So as the molecular size increases, van der Waals forces become
Stronger.
stronger or weaker if you got bigger size.
Weaker. Weaker.
If talk about van der Waals,
Stronger.
Stronger.
okay, kita revise sikit Tadi yang ini untuk strength of metallic bond. Sekarang awak punya force sudah tukar. Kalau van der Waals forces ada berapa faktor? 1, 2, 3. We have the factors of polarity, which refer to the dipole-dipole because it's underneath van der Waals. Okay. Kalau untuk London forces saja, kita ada faktor polarizability, which refer to your molecular size. Bigger the size, stronger the force. Or in other words, we can talk about the factors of the shape. So dekat sini faktor apa? What is the factors?
Polarizability.
Polarizability or the molecular size. Okay, so when the molecular size increases, your London forces or the van der Waals forces become stronger. Okay, lagi besar force dia lagi kuat. Okay, that's why you have to make sure you know what is the forces inside them. Metal, metallic bond. And then for the simple molecule like the group 17, van der Waals forces. Then we compare the factors of it. Okay, so more energy is needed to overcome the forces of attraction, melting and boiling point. What is the trend? Increase or decrease?
Increase.
Increase.
Increase. Because now the forces become stronger going down the group, right? So from fluorine to iodine. Okay, so the last one, F to I, we following your element. But when we talk about boiling point, following the structure, because you want to figure out what is the forces in them. So I can jot down, yeah? So any questions for the trend down group 1, down group 17? Tak ada soalan.
No.
Okay. If no questions, here's only 2 questions that Madam requested into GC, yeah? The first one question is like the answer just now. Sodium to aluminium, silicon, and then phosphorus to argon. So you see how they ask the questions, yeah? Based on the bonding and the structure of elements, explain why boiling point rises from sodium to aluminium. Explain why silicon has the highest boiling point among the third period elements. And explain why boiling point of sulfur is bigger than phosphorus, then chlorine, then argon. So all of this refer to the elements in period 3. Okay, then question number 2, sodium and potassium both element group 1. So write the electronic configuration, subdivision for you, and explain which element is expected to have higher melting point. So question number 2, link it to metallic bond. Question number 3, magnesium, silicon, sulfur. Okay, so if you can see over here, melting point difference for all of them. Silicon has the highest, sulfur has the lowest. So explain what is the structure in them. Magnesium having metallic bond, and then explain. Silicon has the giant network covalent structure, then explain. Okay, sulfur exists only as S8. So what forces for them? So also you can write in the table. Boleh keluarkan table, tak ada masalah. Okay, so explain differences, melting point of 3 of this element. Okay, so submitted into GC. Answer, you can check it afterwards. After the deadline is due lah, Madam will upload. Okay. So we take a 2 minutes break. Anyone want to go to the toilet? Go to the toilet. We'll continue at 2 minutes. We'll continue at 12. Now it's 12. What time is now? 12:10, yeah? I will come back at 12:15. 5 minutes lah. Okay. Those who want to go to toilet, you want to drink water, go. The rest of you can get ready with the notes for chapter 5, yeah?